Welcome back, guys. In this teaching video, I'm looking at part 2 of 7.4 static or rigid bodies. I'll be going through hinges and I'll be covering exam style questions involving equilibrium. We know that when a body is in equilibrium, two conditions are satisfied. Number one, the sum of clockwise moment is equal to the sum of anti-clockwise moment. Number two, the resultant force horizontally or vertically is equal to 0. There are two different scenarios. Scenario number one, beam supported by a string. Scenario number two, beam supported by a rod. Now for a string we have a tension force, for a rod we have a thrust force. Let's start off by looking at beam supported by a string. There are three different cases, 1, 2 and 3. In each of these cases the beam is smoothly hinged at the point H on the vertical wall as shown. Now that hinge is going to release a reaction force on the beam. This reaction force will have component forces, horizontal and vertical. I'm going to explain how to label these horizontal and vertical components. Let's start off with case number 1. If we take moments about the point A, all the forces coming out of A will be neglected. So the only force that I'm looking at is the weight mg. Now that weight mg is going to take the whole body anti-clockwise. So the vertical component of the reaction force released by the hinge on the beam has to act upwards. Because if I hold my pen at the point A, this particular force will now take the body clockwise. So anti-clock has to equal clock to maintain equilibrium vertically. Right, the tension force has a horizontal component acting to the left. So the horizontal component of the reaction force released by the hinge on the beam has to act to the right. We can call it X, to maintain equilibrium horizontally. We can now form a right angle triangle. So here is my right angle triangle. This part is X, this part is Y. This is my resultant reaction released by the hinge on the beam. We can write the resultant reaction as a vector. So it will be Xi plus Yj. Let's look at case number 2. Now the point A is at the center of the beam. We're going to take moments about the point A. So all the forces coming out of A are neglected. So there is no vertical forces acting on the beam now. Hence, there will be no vertical component of the reaction force released by the hinge on the beam. Because if there was a vertical component of the reaction force released by the hinge on the beam will no longer be in equilibrium. Right, for the tension force, the horizontal component is acting to the left. And so, the horizontal component of the reaction force released by the hinge on the beam has to act to the right. We can call it X, to maintain equilibrium horizontally. So we have the following. Okay, that there is my diagram. The resultant force R can be written as a vector. It will just equal Xi. Okay, let's have a look at case number 3. Now the point A is acting less than halfway through the beam. Okay, if I take moments about the point A, all the forces coming out of A are neglected. So the only vertical force that I can see is the weight. If I hold on to the point A, the weight is going to take the beam, or you could say the whole body, clockwise. Okay, so the vertical component of the reaction force released by the hinge on the beam has to act downwards. Because if I hold on to the point A, that force is going to take the whole body, or you could say the beam, anti-clockwise. So clock equal anti-clock, keeping the beam, or you could say the body, in equilibrium vertically. Let's have a look at the tension force. The horizontal component is acting to the left, and so the horizontal component of the reaction force released by the hinge on the beam has to act to the right. We can call it X, to maintain equilibrium horizontally. We can form a right angle triangle. So here is my right angle triangle. Okay, so here is my resultant reaction released by the hinge on the beam. We can write it as a vector. So that will be Xi minus Yj. That there completes scenario number 1. Let's move on to scenario number 2. Beam supported by a rod. Now here is my rod. The T represents the thrust. Okay, if I take moments about the point A, all the forces coming out of A are neglected. So the only vertical force that I can see is the weight. So if I hold on to the point A, the weight is going to take the whole beam, or you could say body, clockwise. Okay, clockwise. And so the vertical component of the reaction force released by the hinge on the beam has to act downwards. We can call it Y. Because if I hold on to the point A, that particular force will take the whole body, or the beam you could say, anti-clockwise. Okay, the horizontal component, T cos theta, is acting to the right. To maintain equilibrium horizontally, the horizontal component of the reaction force released by the hinge on the beam has to act to the left. We can call it X. Okay, and now we can form a right angle triangle. Here's my resultant reaction. We can write it as a vector. It will just be minus xi minus yj. Okay, that's how you label the horizontal and vertical components of the reaction force released by the hinge on the beam. Here is exam style question 1. So we've got a uniform beam AB. The mass of the beam is 2 kg. It is freely hinged at one end A on a vertical wall. The beam is held in equilibrium by a rope attached at D and C as shown. We're going to model the beam as a uniform rod, which means that the weight of the beam has to act at the center, splitting the overall distance into 2 equal parts. We're going to model the rope as a light inextensible string. The tension in the rope is 63 newtons. Part A, find the length AB. I'm going to start by labeling all the distances and forces acting in this particular beam. Firstly, let's call the distance AB x. So AB is equal to x. Now the weight of the beam is going to act at the center, and that weight is 2g. The weight is going to split the distance x into 2 equal parts, and those 2 equal parts are x over 2. There is a tension force acting in the string, and that tension force is 63 newtons in this direction. We can label the component forces for that tension force by constructing a right angle triangle. Alternate angles are equal, so if this is 30, this is also 30. We can put in the arrows. This is your opposite, so it will be 63 sine 30. This is your adjacent, 63 cos 30. Now we need to label the component forces for the reaction force released by the hinge on the beam. So we will take moments about the point C. If we take moments about the point C, all the forces coming out of C are now neglected. So the only vertical force that I can see is the 2g. So if I hold on to the point C, the 2g is going to take the whole body clockwise. So the vertical component of the reaction force released by the hinge on the beam has to act downwards. We can call that Y. Now, if we look at the tension force, 63 newtons, the horizontal component, 63 cos 30, is acting to the left. So, the horizontal component of the reaction force released by the hinge on the beam has to act to the right to maintain equilibrium horizontally. Okay, so we can label it over here, X. Perfect. Right, now, how do I calculate the length AB? How do I work out X? Well, I know that if the uniform beam is in equilibrium, 2 conditions are satisfied. The first one is that the sum of clockwise moments is equal to the sum of anti-clockwise moments. Second condition, resultant force horizontally or vertically is 0. Now I'm going to use one of these 2 conditions in order to work out the length AB, the value of X. Right, now what I want to do, ladies and gents, is eliminate this capital X and this capital Y. They're unknowns. So I can take moments about A in order to work out the lowercase x, the distance AB. So for part A, I'm going to take moments about A. What does that mean then? Well, we know that the uniform beam is in equilibrium, so sum of clockwise moment is equal to the sum of anti-clockwise moment. Right, so if we take moments about the point A, the only forces that we're dealing with is the 63 newtons and the 2G force. Right, so in what direction does the 2G force take the body? Well, it's going to take the body in the clockwise direction. So we can calculate the moment of this particular force. The moment is force times perpendicular distance, so it will be 2G multiplied by the perpendicular distance, x over 2. Remember, that is the perpendicular distance to the force, equal to. Now, if we look at the 63 newtons, if I put my pen at the point A, the 63 newtons will take the whole body anti-clockwise. We need to apply the formula, moment is equal to force times perpendicular distance, to find the moment of that 63 Newton force. The issue is that 63 Newton force is at an angle of 30 degrees to 0.14. So that distance 0.14 is not perpendicular to that force 63. But what we can do is maybe just look at the vertical component of that force 63 newtons. The vertical component is 63 sine 30, and what we notice is that 0.14 is perpendicular to that component. So we can take this force and multiply by the perpendicular distance to that force, which is 0.14. So we have 63 sine 30 multiplied by 0.14. Okay, so we can clean this up. The 2's cancel out. We have gx is equal to 8.82 sine 30. So now we can make x the subject, and if we do this, we get 8.82 sine 30 all over g, where g is equal to 9.8. So if I put this into my calculator, I get x equal to 0.45 meters. Therefore, the distance AB is equal to 0.45 meters. And that there, ladies and gents, completes part A. Now part B, find the magnitude of the resultant reaction of the hinge on the beam at A. Okay, so what we can do is first of all form a triangle. So here is my triangle. The resultant reaction will act in this direction. Okay, so that is R. We can actually form a vector. The vector for the resultant reaction will be xi minus yj. What we want to do is calculate the magnitude. Okay, we want the magnitude, okay, of the resultant vector. To calculate the magnitude, we need to first work out x and y. We know that resultant force horizontally or vertically is 0. So first of all, I'm going to resolve horizontally. So if I resolve horizontally, I know that the resultant force F is equal to 0. So what would that be? Well, that will be x minus 63 cos 30. So x minus 63 cos 30. That must equal 0. So x is equal to 63 cos 30. We can put this into our calculator, and if we do this, we get x equal 63 root 3 all over 2. Okay, so we've got x now in exact form. Now we're going to calculate y. Y is acting in the vertical direction, so we're going to now resolve vertically, taking upwards to be the positive direction. For example, the resultant force F vertically is equal to 0. So what would that resultant force F be? Well, it will just be 63 sine 30 minus 2g minus y. Okay, so now we can make y the subject. So we get y is equal to 63 sine 30 minus 2g, where g is equal to 9.8. So we can put this into our calculator, and if we do this, we get y equal 11.9. Okay, so now I can write down my complete vector R, the resultant reaction released by the hinge on the beam at the point A. So that resultant vector will equal xi, so 63 root 3 over 2i minus 11.9 j. Okay, so now we can find the magnitude of this particular resultant vector. So the magnitude, ladies and gents, is given by the square root of the I component, 63 root 3 over 2 squared, plus the j component, minus 11.9 squared. Okay, so if we put this into our calculator and we round off to 3 significant figures, we end up with 55.8 newtons to 3 significant figures. And that there, ladies and gents, completes part B of the question, which was to find the magnitude of the resultant reaction of the hinge on the beam at the point A. Here is exam style question 2. So we've got a uniform rod AB. The distance A to B is equal to 1.5 meter and the mass of the rod is 3 kg. The rod is smoothly hinged at the point A as shown in the diagram. It is held in equilibrium by a light strut CD. Part A, find the thrust in the strut CD. So first of all, that thrust is going to act in this direction. We can call that T. Now for that thrust we have component forces. We can construct a right angle triangle. Put in the arrows. And then we have a look at this triangle over here and we notice that these two sides are the same. So we have an isosceles triangle. So if this is 90, 180 take away 90 is 90, split 90 into 2 parts, 45. So this is 45. This is also 45. Okay, so we have that alternate angles are equal. So if we look over here, we've got a Z shape. If that's 45, this is also 45. This component over here is the opposite, so it will be T sine 45. This component over here is the adjacent, so it will be T cos 45. Now the weight of the rod is going to be 3g, where g is equal to 9.8. That weight acts at the center, so we can call that 3g. Now the 3g is going to split the distance 1.5 meter into 2 equal parts. 1.5 divided by 2 is 0.75. So this part over here is 0.75 meter. We've got 0.5 meter used up, so this remaining portion here is going to be 0.25 meter. Okay, now if I take moments about the point D, all the forces coming out of D will be neglected. So the only vertical force that I can see is this force over here, the 3g. If I hold on to the point D, the 3g, the weight is going to take the whole body clockwise. And so the vertical component of the reaction force released by the hinge on the rod will therefore act downwards. So I can label that as Y. Because if I hold on to the point D, that force is now going to take the rod anti-clockwise. So anti-clock equal clock, maintaining equilibrium vertically. Okay, let's have a look at the thrust force. Now for the thrust force, the horizontal component acts to the right. And so the horizontal component of the reaction force released by the hinge on the beam has to act to the left to maintain equilibrium horizontally. So I can label that over here, X. This here is my complete force diagram and I've labeled all the distances. Right, so in part A, we want to find the thrust in CD. Now we know that the capital X and the capital Y are unknowns. What we want to calculate is T. To eliminate the X and Y, we need to take moments about A. So we're going to take moments about A. What do we know about a body being in equilibrium? Well, number one, the sum of clockwise moment is equal to the sum of anti-clockwise moment. And number two, the resultant force horizontally or vertically is 0. So in part A, I'm going to be using that first condition. Sum of clockwise moment is equal to sum of anti-clockwise moment. So taking moments about A is going to allow for neglecting all the forces acting at A. So X and Y are eliminated now. So the only forces that I have is the thrust force and the weight force. I need to calculate the moments of each of these. Holding on to the point A tells us that the weight is going to take the body clockwise and that thrust is going to take the body anti-clockwise. So let's start off with the clockwise moment. So the moment of the weight force 3g is going to be 3g multiplied by the perpendicular distance to that force. So that perpendicular distance, ladies and gents, will be 0.75. This must equal the moment of the thrust force. Now, if you look at the thrust force, the distance 0.5 meter is at an angle 45 degrees to the thrust force. It's not perpendicular to the thrust force. So what we can do is maybe perhaps just look at the vertical component of the thrust force. So that vertical component is T cos 45, as you can see from the diagram. So that force T cos 45 multiplied by the perpendicular distance to that force, which is 0.5. So what we have is T cos 45 multiplied by 0.5. So now we can make T the subject. So T is equal to 3g times 0.75 all over 0.5 cos 45. Okay, so we can put this into our calculator and then we can round off to 3 significant figures. So if we put this into our calculator, we get 62.4 newtons to 3 significant figure. So that there is the thrust in the strut CD. Let's move on to part B. So in part B, it says find the magnitude and direction of the force exerted on the rod AB at A. In other words, the force exerted by the hinge on the rod AB. So we can form a right angle triangle to represent the resultant reaction released by the hinge on the rod. Okay, so we've got these components. Let's form a right angle triangle. So that there is my resultant reaction. I can write it as a vector. This would be minus xi minus yj. So our target is to work out the magnitude of this resultant reaction. That is our target. Well, first of all, we need to work out x and y. So if I start off by working out x, which is acting in the horizontal direction, I can resolve horizontally, taking right to be the positive direction. The resultant force F acting horizontally is equal to 0. Okay, so what would that resultant force F be? Well, we have T sine 45 degrees minus X is equal to 0. Okay, so we can rearrange and make X the subject. X is equal to T sine 45 degrees. But we know what the exact value of T is. The exact value of T is given over here. So X is equal to 3g all over 0.5 cos 45 multiplied by sine 45. So if I put this into my calculator, and if I round off to 3 significant figures, I get X equal to 44.1 newtons. Right, so I've got X, now I'm going to work out Y. To find Y, I'm going to resolve vertically, taking upwards to be the positive direction, for example. Now, the resultant force vertically, you can call that F, is equal to 0. So let's form an equation. What is that resultant force F vertically? Well, it will just be T cos 45 minus 3g minus Y equal to 0. Okay, so we can make Y the subject. So Y is equal to T cos 45 minus 3g. We know the exact value of t is over here. We can substitute that in to work out the value for y. We're going to multiply this by cos 45 take away 3g, where g is equal to 9.8. Okay, so g is equal to 9.8. We're going to substitute that in, put this whole thing into our calculator, and if we do this, we end up with y equal to 14.7 newtons to three significant figures. Okay, so I've got my x, I've got my y. Now I can write down the complete vector for the resultant reaction. So that complete vector r is going to equal minus x, so minus 44.1 I, minus y, which is minus 14.7 j. Now we can work out the magnitude of this resultant reaction. So we can calculate the magnitude. I'll just write it over here. That would just be square root minus 44.1 squared plus minus 14.7 squared. And if we put this into our calculator, rounding off to three significant figures, this gives us 46.5 newtons. Okay, that ticks off the magnitude. Now we need to find the direction. Okay, so if we go back to this diagram over here, we formed a triangle. For that triangle, we've got the lengths. This part over here was your x, which is 44.1. And this part over here is your y, which is 14.7. What we're trying to do is working out this theta, the angle. Whenever it's a direction, you're trying to calculate the angle. So over here, we can use tan theta is equal to opposite over adjacent. So 14.7 over 44.1. So theta is equal to tan inverse of this. All right, so if we put this into our calculator, we get 18.4 degrees to three significant figures. So for the direction, we have theta equal to 18.4 degrees below, I repeat, below the horizontal AB, okay? Below the horizontal AB. That is your direction. Okay, so ladies and gents, that is the end of exam style question 2. So ladies and gents, in summary, whenever you have a hinge question, if you want to determine the correct direction of the horizontal and vertical components of the reaction force released by the hinge on the body, what you need to do is take moments about the point where the string is attached or where the rod is attached. That will help you determine the correct directions for your horizontal and vertical components. Like always, if you found this video useful, please don't forget to leave a like, leave a comment, subscribe to my channel, turn on the notification bell so that you get updates whenever I release teaching videos.